This video is sponsored by Brilliant, more about it later. In this video we will look at how regular, normal-sized portals can create infinite recursive space. We will use them to create really beautiful structures. Then I'll explain how it works, and then represent them as teleportation surfaces. And at the end, we will even understand a bit of portal topology. In the last video, many of you asked me to make the camera visible. I've added it. This is the camera, or you could say it's you, the viewer. You will see it in the main scenes, but not in all of them, since I have to program it differently for each scene. So I hope you will cut me some slack here. In the last video I showed what happens when you place a small portal inside a large one. You get a pocket dimension. And we did this using a curved portal surface. The whole construction was based on one portal being smaller than the other, so the surface of one part could fit inside the other. This raises a question: is it possible to pull off the same trick when both portals are the same size? Because when you enlarge the small portal, its surface will also enlarge and eventually it won't fit and everything will break. It is possible, and here's what it looks like. And now we get a fair infinite space. But how does it work? So, there are two concepts for calculating portal-through-portal teleportation. The first is teleportation degrees, where we create copies of the portal and filter their parts. I explained this in detail in this video. The second way involves creating a clever teleportation surface that never intersects the portal, and we don't have to teleport anything or create copies. The issue is that first method works great in almost all cases, but breaks when we try to place a small portal in a large one. The second method works for a small portal in a large one, but it's very limited. It's unclear how to program these surfaces to work in the general case. So next, I will explain how I improved the first approach with teleportation degrees so it works for a small portal in a large one too. But before I get to that, I want to say that for surface approaches, I will use two-sided portals, because that's their natural state. And for teleportation degree approaches, I will always use one-sided portals, because it's easier to program and it gives you less visual noise. You can imagine it's actually a two-sided portal that just has its back covered. Let's recall how the teleportation degrees approach works. First, we take two coordinate systems that will define our portals, and then place these portals at these locations. If we send one portal into another, then nothing happens when they intersect, because we didn't yet program any behavior. We can see there is an extra part behind the orange portal that technically entered the portal and should be teleported. Actually, if you think about it, we never need anything behind the orange portal. So for all future parts, I will write code to remove them when they go behind the orange part. So we have our first break above the portal. It can be fixed if we continue the blue part here. To do this, we teleport the coordinate system of the entering portal from the orange portal to the blue portal and get a new coordinate system. I call this the second teleportation degree. We can place a new portal on it. Here we see this new part looks okay, but we need to remove the back part behind the blue portal. We remove it and now everything works. We move further and have a break again. To get a new teleportation degree, we need to teleport the second teleportation degree from the orange portal to the blue one, and we get the third teleportation degree. Then we do the same operations, add a new teleportation degree and filter it. So the algorithm is that when the portal image breaks, you need to add a new teleportation degree. And with this approach, you can add them infinitely. Only those that do something useful will be visible. I want to say that this teleportation degree approach works perfectly as long as our portals are the same size and as long as they don't intersect boundaries. No matter how hard I tried to place a portal inside itself without hitting a wall, I couldn't do it. By the way, In the last video I said I created all teleportation degrees manually, but now they are generated automatically and there can be as many as needed. Now let's look at small portal entering a large one. And this is where it breaks. And the problem is that new teleportation degrees won't help here, because all these teleportation degrees are behind the orange portal and they all get filtered and disabled. This is exactly where I gave up in the past, because I couldn't imagine that it was possible to fix. But now we have hemispherical portals which can give us a clue to the solution. My plan was to take screenshots at the same camera angles and figure out what's happening and how to program it. And here's what I understood. First, a new type of break happens when this small blue part enters its larger version, and it enters completely, not partially. Also, before, portals were exclusively outside and didn't create a new space. But now, with these hemispherical portals, we get something like a separate space. So if we want to simulate this with flat portals, we have no choice but to program a separate space with a black background at this new break location. So the new break becomes a portal to a black pocket dimension with only this one part visible. Okay, so what should be in this space? When I looked at the screenshots, I realized all the teleportation degrees of the entered part should be there. Okay, I implemented this, and let's compare the images with the hemispherical situation. Some portals are missing. I increased the number of rendered teleportation degrees, but nothing appeared. And here you can see we need teleportation degrees in the reverse direction. Or in other words, we need negative teleportation degrees. Previously, I teleported the blue portal from the orange portal to the blue portal and got new teleportation degrees. And these were portals that could be seen through the blue portal. But what about portals visible through the orange portal? What if we teleport the orange portal through the blue portal? Then we get different portals, and these are the ones that go in the reverse direction and fit this situation. After adding them, the new approach starts working identically to hemispherical portals. Before, negative teleportation degrees weren't needed because the blue portal was teleported by the orange one. But here, two teleportations happened at once. Blue teleports orange and orange teleports blue simultaneously. Look, this small part enters its larger version, but you could also say that part of the large one enters the small one too. And on the outside, there are only positive teleportation degrees, while the pocket dimension has all the teleportation degrees from minus infinity to plus infinity. Now we have a working approach, and we are not limited by any surfaces and don't need to program them, expand them, and so on. And of course, we can make a normal sized portal inside, and it works. We fly inside and see that nothing intersects with anything. Everything looks correct. We can revolve around however we want, and the portals go in this infinite line. You might be wondering how I am able to figure out such things. The secret sauce is this visual scene editor, where I can add an object or portal and then play with them to get immediate feedback on what works and what doesn't. And this is a good way to solve problems and understand the topic. This is why I am happy to introduce you to this video's sponsor, Brilliant. Brilliant helps you become a better thinker and problem solver with thousands of visual, interactive lessons in math, science, programming, data analysis, and AI. To develop the skills for building visualizations like mine, I highly recommend their courses on vectors and programming. The latter will help you think like a programmer and get familiar with Python to start programming right away. What I love about Brilliant is that it focuses on problem solving. And I've always believed that this is the best way to build real understanding. Plus, their mobile app lets you learn at any time and any place. Except maybe for the pocket dimension. Use Brilliant just a few minutes a day to sharpen your problem-solving skills. To get started, go to brilliant.org/aptazoraks. You can also click the link in the description or simply scan this QR code. By doing so, you'll get a 30-day free trial plus a 20% discount on the annual subscription. Thank you, Brilliant, for sponsoring, and now back to the portals. Let's experiment with this framework. Let's take this object and enlarge it forward until it collides with something. We see it can enlarge infinitely and doesn't intersect with anything. We fly in, and inside we see a huge space without end. That's why it's so dark here. So we can say that real infinite space is created here. And this isn't the same as in the previous video, when scaling portal can fit infinite space in a finite volume. Now let's place a small portal inside. Fly in here and try to scale it up to normal size. This works continuously and it seems like we can continue further. We do it and it surprisingly works. It turns out with this approach we can place a large portal in a small one too. A completely counterintuitive result that actually works. And this looks symmetrical to the process of placing a small portal in a large one. Next, let's just look at the beautiful picture. Let's take this combination of large and small portals. When we place one in the other, we see how many teleportation degrees come out of the blue portal in the shape of a shell. And this is what it looks like from the pocket dimension. We get an infinite logarithmic spiral. By the way, that little spiral of white spheres represents the camera. Now let's gradually change the scale to normal. We get an infinite vertical spiral, a very beautiful and massive structure. And let's also look at this animation of how the portal scale changes from large to normal and vice versa. Thanks to no restrictions on the teleportation surface, we can play around here and get lost in it for hours. As a reminder, you can visit my web demo and play with this yourself. Add this link in the description. And how will an object look in such space? We place it and it looks normal. The cube just goes along a straight line. But inside, the cube also repeats from minus infinite teleportation degree to plus infinite. Here space is looped in such a way that one object looks like many objects. Now I want to show what's forbidden to do with portals. Let's move the small portal to a face-to-face position. And then inside we scale the portal to normal size. We fly inside and see an infinite line of portals. But what if we rotate it? We see the line turns into a circle that infinitely intersects itself. This configuration is invalid because at some point the distant teleportation degrees start intersecting the backs of existing portals. And all infinite teleportation degrees lie in one finite circle. And if they had any thickness, they couldn't fit here. That's probably why this is an invalid configuration. Before, with the portal in portal configuration, we were only limited by portal boundary intersections. But now in this pocket dimension, there are more complex restrictions that I can't formulate yet. And now about teleportation surfaces. As I said, there are two approaches: teleportation degrees and special shapes of teleportation surfaces. I generalized teleportation degrees to a pocket dimension, where a normal-sized portal works. But how to do the same with teleportation surfaces? I thought about it for a long time and found a solution. Let's look at following 2D animation. We have a small portal and we place it in a large one. To make this work, we need to bend the surfaces so they don't intersect. Next, we've inserted it and want to scale it up. We scale it and the surfaces need to scale accordingly. And if you do this in a clever way, the surfaces will turn into infinitely extended parallel lines. This is the solution to how to represent a normal-sized portal as a teleportation surface. And this animation was suggested by several users in my Discord server. So here are two normal-sized portals with an infinite surface beyond the portal. If we rotate around these portals, we teleport to their outer side, and it looks like there's nothing between them. The portals are parallel, so their planes are also parallel and don't intersect. With flight teleportation, you can see the black pocket dimension. If we fly inside, we see the familiar line of portals. And if we turn off light teleportation, we can see how the entire pocket dimension simply lies between two planes. This explains why there's real infinite space, why an infinite rod can fit here. It borrows an infinite piece of space from the originally infinite Euclidean space. But what is that strange white line? We turn off light teleportation and see that this line is at the boundary where the two infinite portal planes converge. Actually, this happens because the ray teleports indefinitely between these boundaries. And due to limited floating point precision in computers, at one point the error becomes larger than the distance between these infinite planes, and the ray escapes beyond the surface. So it's just a rendering artifact, nothing more. But such negative surface works well when our portals are parallel. But what if we want to rotate one portal, for example like this? Then the portal surfaces will intersect and it won't work. But we can orient planes in such a way that they become parallel again. And as you may notice, I also use sphere pieces around the portal to maintain surface continuity. And the picture inside looks familiar. But here the rendering artifact is much larger. The next scene is this spiral inside the pocket dimension. And outside it's represented by these parallel planes. But how to find the plane tilt angle for different portal rotations? When portals are parallel, the plane normals are also parallel. Then, when we rotate the portal, the plane normals stop being parallel. And then, when we reach the right tilt angle, the normals become parallel again. So we need to find such a normal vector that is parallel to its version after teleportation. Let's write this mathematically. The next part is for people who had linear algebra in college. Don't worry if you don't understand, it's not very important. As I said, portals consist of two coordinate systems. And each coordinate system can be written as such coordinate transformation matrix. Then teleportation of a normal vector can be written like this. First we transform the vector to local coordinates of the orange portal, and then transform them from the coordinates of the blue portal. And after all this, the normal should equal to itself. Looks familiar. If we put brackets around the matrices, this becomes an eigenvector of this matrix. And this is the first time in my life when eigenvectors were useful to me. It turns out that this eigenvector of the teleportation matrix is the normal vector, which can then be used to calculate the portal surface. Next, I want to show how such negative portal looks like in my space curvature simulation program from the last video. Quick update, previously there were holes here, but I've now fixed them and the surface became continuous. So this is a negative portal scene. Here a green square moves outside this portal, a blue square moves in a circle in the pocket dimension, and the red one moves in both spaces. The top and bottom go to infinity. We run the simulation and it converges to this shape. On it we have a regular plane and a separate cylinder, and both are connected by portal tunnel. So when we are inside the pocket dimension, we are here in a separate cylinder, and it's no wonder why rays loop and it looks so dark. And the regular space outside is here when the green square moves. So the pocket dimension is really a separate entity that's connected to the regular world by a small portal tunnel. And finally, the question that's probably been bothering this whole time. Is it possible to place a normal-sized portal inside itself without shrinking it, in such a way that it forms infinite space? Because before, I always first shrunk it, then inserted it, then scaled it back up. Yes, it is possible, but if your portal has an infinite surface. For example, this portal has an angle shape, and its other part goes infinitely down left. You can just move the portal down and to the left, it will fit since it's infinite, just like in Hilbert's hotel. There's the pocket dimension. Okay, but what if the portal has a finite boundary? The problem is that no matter how much I tried different positions, of portal in portal, I couldn't find one where I could insert it. I even made this interface where you can change the surface, add, remove pieces in different places. But I still couldn't find that position. But maybe subportals, which I proposed in this video, will come to our rescue. Look, when a portal enters another, it gets stuck here. What if we place a new portal here that will prevent this collision? Let's try. So there's this subportal. Here its entrance and there's its exit. We move the portal exactly the same way and now it doesn't get stuck. It can move further. We move more and look. Now we are limited by this place. The blue portal will hit the boundary of the subportal. But it is in such position that now we can move the subportal through the blue portal. It can continue moving the large portal. And this is the maximum I've reached. I don't know how to proceed further, too many variables appear. So friends, I actually don't know if this is possible or not, but it was worth giving it a shot. And now I want to try to answer the same question from a topology perspective. Topologically, an infinite 2D plane is equivalent to a sphere with one punctured point. I think this is somehow related to the stereographic projection. And a regular portal is equivalent to a plane with one hole. So a regular portal is equivalent to a torus with a punctured point. Next, a cylinder is equivalent to a sphere without 2 points. And a negative portal is a plane connected to a cylinder. So it is equivalent to a sphere with 3 punctured points. So if we compare a regular portal and a negative portal with a pocket dimension, they are topologically not equivalent to each other. And since regular portal movements should preserve topological space equivalence, this can probably serve as a proof of why one portal can't be placed in another without shrinking. But I'm still not sure about this, since scaling should also preserve topological space equivalence, but somehow it breaks everything. And now the answer to one of the most frequently asked questions from the last video. What if you place an object in the pocket dimension and then pull it out? So there's an object here and a face-to-face portal. We fly in here and move the portal inside itself to create a pocket dimension. Now we can move the object inside. You can see it's fully inside the pocket dimension, beyond the portals. Next we pull out the portal and see that the object also came out. So the object can't actually get lost in the pocket dimension. It just might become smaller if you push it too far. And it works very simply. I represent the portal as this teleportation surface. Place the portal inside, then place the object inside, and when I pull out the portal, the object stays in the same place. But due to the axiom about surface irrelevance, we can claim that the object is actually here, where we can see it. By the way, initially this video was much more complex. For example, I considered infinite cones instead of planes. I wanted to talk about their complex constructions and properties. But user RareBeef in my Discord suggested using planes, and this simplified the explanation a lot. Also, instead of the topological proof, I originally thought to justify this through the impossibility of a pocket dimension in spherical geometry, but also decided to remove this part as unnecessary, when I came up with the idea that a negative portal can be made in my space curvature program. It's a shame that sometimes this happens. You make a scene, write a script, program animations, and then it doesn't get used. And I wanted to thank all the brilliant people from my Discord server. Your ideas shaped this video a lot. As you can see, these videos take a lot of effort to produce. So if you'd like to support my work, you can join my Patreon. That's all, thanks for watching.